Hey Yasley Panthers, Coach Strong here. I'm going to cover some of the topics we'll be going over the next week of class, which includes distinguishing between elements, molecules, and compounds, and using chemical formulas to count atoms. So first, just a quick review. We have been covering elements for quite some time now, but just a reminder that an element is considered a substance composed of a single atom. It is a pure substance and is the simplest form, so it cannot be broken down into another substance by chemical or physical means. We also are going to be talking about and looking at molecules. Molecules are two or more atoms joined together, and they can be the same or different. These atoms are chemically bonded, so they cannot be separated physically. Some examples of molecules would include oxygen gas, O2, and water, H2O. In both cases, we have at least two atoms. H2O is actually more than two. And O2, it's the same atoms. H2O, it is different atoms. Finally, we will be looking at something called compounds. Compounds are two or more different atoms joined together, but like molecules, they are chemically bonded, so they cannot be separated by physical means. And with compounds, they have different properties than the elements they're made of, because as opposed to being the same, they are different. In this case, here are some examples. Hydrochloric acid, which is hydrogen and chloride bonded together. Carbon monoxide, which is carbon and oxygen bonded together. Another example would be glucose. You should be familiar with that if you've learned about photosynthesis. C6H12O6. In all of these cases, you have two or more atoms and they are different. That would make it a compound. So before we look at the comparison across the board of elements, molecules, and compounds, I also want to mention organic compounds. This is something that you probably have heard of before, but we're just going to review it quickly. Organic compounds are still two or more different atoms combined, but they must contain carbon and hydrogen. There's a acronym we like to use, CHOMPS, with an N, not a M as in Mary, to help you remember that organic compounds include carbon and hydrogen, and they may also include oxygen, nitrogen, phosphorus, and sulfur. Some organic compounds include urea, which is CH4, N2O, glucose, and acetic acid. All of these are considered organic compounds because they have carbon and hydrogen. And we will be doing more practice to where you can successfully identify whether a compound is organic or inorganic in class. So just a quick recap as we compare elements, molecules, and compounds in this lovely table that I've just put together. Elements are single atoms or one kind of atom, so just the symbol, or the one I showed you, O2. In both cases, we're only dealing with one type of atom. Molecules are two or more, and they can be the same or different. So O2 is two of the same. That is considered a molecule. H2O, two or more different atoms combined. And then we have compounds, which must be different. So H2O would be considered a compound. And I gave you the example of glucose. As you look at these and compare, there's one thing that I want you to keep in mind. We'll be discussing it in class. All compounds are molecules, but not all molecules are compounds. Write that down. See if you can understand what that means, and if you can explain it, it is something that we will be discussing in class. Now let's move on to chemical formulas. So a chemical formula is a combination of symbols that shows us the composition or makeup of a compound or a molecule. Every single substance has a chemical formula, and it can include elements, symbols, it can include subscripts, and coefficients. And the information that we can get from a chemical formula, like say H2O, or in fact 3H2O, would be the types of elements that are in the substance, the number of atoms of each particular element, the total number of atoms regardless of what element it is, and the total number of molecules or compounds. But before you can figure that out, you got to know the difference between a subscript and a coefficient and the information that each of those things tells us. Okay, so starting with subscripts, which are these tiny little numbers in blue. They are written after a symbol, and they will be slightly below and smaller. Those tell us how many atoms of each element there are. If you do not see a subscript, we assume that the number there is 1, and it only applies to directly what's in front of it. So each of these 2's only applies to the letter directly in front of it, like that. Now if we're dealing with parentheses, which we will do an example of later, anything inside the parentheses, the subscript will apply to that as well. Then we have coefficients. Coefficients are these large red numbers. They are written in front of chemical formulas, and they tell you how many molecules you have of a substance. If you don't have a coefficient, like there is one missing here, then it is assumed, that's my terrible question mark, that there's a 1 there. And these apply to everything behind them until you get to a sign like a plus sign or a yield sign. Okay, so when we're counting atoms in a chemical formula, we're going to end up multiplying the coefficient by the subscript to get the total number of each atom, and then you're going to add up those to get the total number of atoms. But let's start with something simple. We have O2. Remember that your subscript applies to everything in front of it, so that 2 applies only to the oxygen, which means I have 2 oxygen atoms. Alright, now when I've only got a coefficient, that applies to everything behind it. Remember, if I don't have a subscript, I assume that there is a 1 there. So I have 3 oxygen atoms. When we put those together, we multiply. So I have 2 oxygen atoms, but I have 3 sets of that, so I do 3 times 2, and I get 6 oxygen atoms. Now I wanted to give you one example of parentheses before we end the video. So here we have lead nitrate. Remember, as I stated earlier, the subscript applies to everything inside the parentheses. So that 4 applies to nitrogen and oxygen. I don't have a subscript next to my lead, so I have 1 lead atom. I have 4 nitrogen atoms because I don't have a subscript immediately next to my nitrogen either. And I have 12 oxygen atoms because I have 3 directly next to it, and there are 4 sets of those because of the subscript outside, which makes my total number of atoms 1 plus 4 plus 12, which is 17. If this is making sense to you, awesome. You're on a good start. And if not, have no fear. We will be practicing this plenty in class. Remember to take good notes. If you have any questions, do not hesitate to ask your teacher, and watch this as many times as you need to. It's always available for you.